welcome to another episode of Fast Talk. Rob, it is just you and me here alone on a chilly fall morning.
It's been a while. We should have a fire going, some blankets, reading podcasting. We should be podcasting right now.
Yeah, we need a little fireplace in this. This would be kind of fun.
And dangerous.
Yeah, it would be.
It would be dangerous.
Yeah. So I don't know about my mental state this morning because I will admit I was a little late because I got up. I was rushing to get to this recording. I realized I needed to take my garbage out. I took all my garbage out, then realized it was Wednesday, not Thursday, and took all my garbage back in, and then was late. I went, that's kind of where my brain is at today.
But Wednesday is garbage day at the office. And so in approximately 15 minutes, there's a garbage truck that's going to be going by our window.
Yeah,
so
we do like to record Wednesday mornings on the garbage truck.
I love recording Wednesday morning. It's my favorite morning to record.
There we go. I actually like it too.
Hey, it's chilly this morning, Trevor. You rode your bike into work?
I did.
I pulled in the parking lot and cursed you out. I was like, this jerk never shows up on time. And then you were sitting here. So I figured you rode your bike.
I rode my bike. I actually spent the entire weekend completely rebuilding my bike because the brake was broken. The handlebar tape was gone. The tires were gone. The wheel needed to be rebuilt. It was basically a death trap.
Brakes only slow you down.
Yeah, that's fair.
Do you know what speeds you up?
What's that?
Muscle fibers.
And that's what we're talking about today. Good transition, Rob.
I'm proud of myself for that one.
That was a good one. So we're doing a new type of show, and please give us your feedback on this one, whether you like it. But we have heard from people saying you cover really interesting topics, some of the time maybe, on what's new, what's current, what's going on in training, in the science. But often we refer to things like muscle fibers, and we don't really explain what that is. So we've had this thought about let's do this kind of new series of just the basics. Let's go back, cover some of these fundamental things that you really need to know in order to understand what we're talking about in training science, and just kind of have some fun covering it. I hope this doesn't turn into a physiology 101 lecture that puts everybody to sleep. Hopefully, Rob and I can give you some good, interesting information, but keep it fun, keep it entertaining, and teach you a few things along the way.
At the very least, you don't have to sit and watch a professor write this all out on a blackboard.
Yeah, we should just get the chalkboard and make that sound while we're talking.
I just want to say, Tom Swenson, who was my undergrad, physiology teacher at Ithaca College. Thanks, Tom. Legend. Everybody who knows him, he's a legend. The guy could write and talk at lightning speed. It was absolutely incredible. I don't possess those skills. I could never be a professor.
My organic chemistry teacher took pride in the fact that he had one of the lowest grade point averages of any orgo course in the country.
Wow.
Like, he wrote the big textbook that a lot of schools use, so he was kind of a big name.
I didn't know sadism was part of organic chem.
What he would literally do, and this is before all the technology days when we were literally on a chalkboard.
Mm-hmm. Yeah.
He would sit there with his right hand writing.
Yeah.
And he would intentionally put his head in front of what he was writing. And then he would have his left hand with the eraser. And he would write and erase at the same time with the intention that half of the class would not be able to see what he wrote.
That's funny. That's funny. Let's see, my physiology. Man, let's just reminisce about old days. It was the dual chalkboards that you could lower and raise, and they would go, so like you would write on one and then like raise it up and be writing on the next one. And I remember Tom would be, Professor Swenson would be writing like so fast and furiously, pieces of chalk would just be exploding out of his hand, hitting people in the front row. I had to sit in the back. I was afraid of losing an eyeball.
Oh, God, the good old days.
The good old days. Now you can just watch a YouTube video or Khan Academy or listen to Fast Talk Labs.
Yeah. So let's go to the good old days and let's get into some good basic physiology. How was that for a transition?
I think that worked.
Yours was better. I'll give you that. Yours was better.
It's okay. In The Future of Coaching, which is the last module release of The Craft of Coaching with Joe Friel, we envision what the future of coaching looks like in the years to come. While artificial intelligence will play a critical role, AI will never completely replace coaching. However, leveraging its attributes to find the right balance of personal connection with automated tasks will be vital to remaining relevant with future generations. Check out The Craft of Coaching Module 14 at fasttalklabs.com.
So we're talking about muscle fibers, and let's get into the really, well, actually put in my notes. Let's cover the boring stuff first and get it out of the way. So here is your absolute basics. All muscles are made up of fibers. Those fibers are not uniform. How am I doing so far, Rob?
I'm picturing them wearing a jacket, except I'm not because I can't picture things.
That's true. You can't. So they're not uniform. You have different types of muscle fibers, and most muscles in your body will have a mix of the different types of fibers. It's not like any one muscle is just going to be all type 1 or all type 2B. It's going to have a mix, but the proportions will vary. So in humans, we have 3 main fiber types, and we're going to dive a little deeper into this in a minute. But it's type 1, also known as your slow twitch muscle fibers. And then you have your fast twitch muscle fibers, and there's 2 types. There's 2A. Now, here's the first interesting thing for you, 2X.
Where the heck did X come from?
Right. You will read all the time type 2B. You will hear people talking about type 2B, but for reasons we'll probably cover in a minute, humans actually don't have type 2B. We have 2X. Thank you. That's what I was looking for. 2B are basically pure anaerobic muscle fibers. So continuing with the basics of the physiology here, we're going to cover what differentiates these muscle fibers, but really think of those slow twitch tend to rely a lot more on aerobic metabolism. Those type 2 fibers tend to rely more heavily, and this is simplification, tend to rely a little more on anaerobic metabolism. When you have a 2B fiber, it's pure anaerobic. Mm-hmm. 2X aren't. They have both the aerobic and the anaerobic machinery. And so I remember reading one of my physiology texts that humans are one of the purest aerobic animals on the face of the planet. And this is the part of the reason why we don't have pure anaerobic fibers. All of our fibers are capable of working aerobically.
There you go. Yeah, the fiber types and how they're found across the body has always fascinated me, Trevor. So I want to touch on that a little bit more.
Please.
If we think about your lower leg, your calf muscle, right? Your calf muscle is actually made up of a few different muscles, with the major ones being the soleus and the gastroc. We don't really need to get into the anatomy of this, but because the soleus is used more in walking, in maintaining balance, it's kind of always functioning at a low level, you tend to find more slow twitch fibers in your soleus. Right. The gastroc is the big outer portion, and it tends to be more involved when you're sprinting, jumping, running, and because of those higher force situations, the fast twitch tends to be more populated there. But what's interesting is if you take a muscle fiber, no matter where it's found, a slow twitch type 1 fiber is the same fiber characteristically anywhere in the body. It can come from your tricep or your big toe. It doesn't matter. Characteristically, they're all the same.
Yep. And I love that you went there because you can contrast humans to rabbits. I remember one of my physiology professors explained this to us, and it was kind of neat. We're capable of walking. We can go outside and just go, I'm going to just do this slow, methodical walk. And that's because we have all those slow twitch fibers that you were talking about. Watch a rabbit even trying to move slowly because
like hyperspeed all the time.
Their hind legs, their muscles are primarily those 2Bs. Mm-hmm. And those fast twitch, really anaerobic muscle fibers are also very strong. Mm-hmm. So a rabbit can't just slow walk, keep it smooth through the field or whatever. It has to hop because those muscles just can't not contract with a lot of force.
Yeah. Well, I'm gonna step outside of our human physiology element here for a second, and I'm sure what I'm gonna say is wrong, but it's gonna sound good enough that people believe me. So if I am wrong, don't write in. I know that this could be incorrect.
I will see if I believe you.
But chickens can fly, right? We don't really think of chickens flying, but they can fly, but they can't fly very far distances. What do we know about chicken breast meat? It's white.
Yes.
And Trevor, why is it white meat?
Because that's your 2B fibers primarily.
You got it.
Right? And they don't need blood supply because they're anaerobic.
They lack a lot of myoglobin. They lack mitochondria. They lack all of these things. And that's what makes them fast twitch, right? And white meat, that also means a chicken can't fly very far because they're not using an aerobic oxidative muscle to do it.
As we all know at Thanksgiving dinner, the white meat is far better.
If it is doused in gravy, I agree.
That's fair.
Yes, but gravy is the best part of Thanksgiving. So we've covered fibers. There's another topic in here, concept that's really important, Trevor, and that's motor units.
Yes. So take it away, Rob.
Me take it away. You take it away. I teed that up for you.
I'm doing fine. Okay.
You're doing so good.
Yeah, you're doing actually good throw. So I got to give you that one. I'll take this one. So these fibers have to be able to get a signal from the brain, or at least from the spinal system, to contract. And the way they do that is there are nerves that connect to these muscle fibers, and they send the signal and tell the fiber, time for you to contract. So what you have in these muscle fibers is motor units or motor neuron units. So basically you have a nerve that comes from the spine that will then branch out, and it will innervate multiple fibers. So I've never actually looked this up, but I don't think you will ever see a one-to-one where you will have a nerve that will just innervate a single muscle fiber. I think they always innervate multiple fibers.
I think that the lowest I've ever seen is a motor neuron innervating like 3 to 4 individual fibers for the very finest motor control. And that might be happening, say, in your eye, if I remember correctly. But oftentimes that nerve is having a lot more fibers contract under its will, under its domain.
Yep. But this innervation, we're actually going to get to this in a minute when we talk about recruitment of muscle fibers. It's really important. But before we get there, let's continue with some of the basics. And by the way, I should have given this qualifier at the very beginning, but I'm going to give this right now. Rob and I were talking about this. We want to explain these basics. And before we started this episode, we were like, when was the last time you just read something straight about muscle fibers?
It's been so long that this episode has scared the bejesus out of me.
I was the same. I actually went back, pulled out a bunch of my textbooks last night and just reread my notes, my highlights from the textbooks. And this is like from 15, 20 years ago. So one thing we're going to say, everything we're talking about, we both have remembered reading. We were taught this, but we were taught this years ago. And there's always this concern of, are we remember this right? So we're going to have this qualifier here of memory is not perfect.
My fear on this is like the chicken thing, that my memory has filled in some blanks in the meantime.
Yes.
And I don't know if I was ever taught some of this or if I'm just talking, pulling it out of thin air. But, this is all well-researched, well-known information. We're not reinventing the wheel on this one, which is sometimes the most dangerous information to share. So,
Yep. And to that point, I have an example of this. I have always told people my college admission essay paper. I've always told people what I wrote about in that paper because I was always very proud of it.
You mean ChatGPT didn't write it for you?
Yeah. No, we were on chalkboards back then, remember? I actually literally typed it on a typewriter when I was applying to college. Yep, that old. So I have always told people what that paper is about. And about a week ago, I actually went back. Somebody was asking me about it and reread it and was like, wow, this is not at all what I've been telling people this paper was for 10 years. I'm like, it was the same general subject, but I remembered it completely wrong. So there's our qualifier. We were taught all this. We could be remembering some of this a little wrong, but still going to be fun. And I'm glad I gave the qualifier here because this is something I remember from college.
Stop hedging, Trevor. Get back to the episode.
Why are they called fast and slow twitch? And here's my big qualifier. I don't think really that's the appropriate names anymore.
Yeah, I'd agree.
So a long time ago, when they were first studying muscle fibers, they did studies on frogs. Mm-hmm. And what they were doing was literally taking the muscles out of frogs, and they would connect them to a little apparatus so that the muscle fiber and the muscle would be hanging, and they'd have a little weight connected to the muscle. I actually can't remember if they took out individual fibers or if they took out the whole muscle. I think it was the whole muscle. And then they would get them to contract.
They'd zap the crap out of them, Trevor.
Exactly. And what they discovered was some contracted really fast, some contracted really slow. Or not really slow, but slower. And so they named them fast and slow twitch muscle fibers because that's what they saw about them. I'm not going to say this is wrong. Yes, these 2X, 2A tend to contract faster than your type 1s, often 2 to 3 to 4 times faster, as I remember. But I would say there's more important characteristics that differentiate these muscle fibers. And why is that important? I remember being on a ride not too long ago and hearing 2 riders talking about at what cadence do you need to be riding at to go from using slow twitch muscle fibers to fast twitch? Because they were thinking it had something to do with leg speed. And if you were pedaling slow, you were using slow twitch muscle fibers. And if you're pedaling fast, you're using fast twitch muscle fibers. And that's why I don't like the terms fast and slow twitch, because that's not at all the way it works.
Yeah, Trevor, I think it is important that you bring this up because, let's be honest, when we're talking fast and slow, we're talking milliseconds for both of them.
Right.
So a fast twitch muscle fiber is contracting in about 7 milliseconds, and a slow twitch, very slow twitch, is contracting in 100 milliseconds, right? It sounds like it's a heck of a lot more, but again, it's still milliseconds. But I do agree that, hey, in the beginning of research, when you're just hanging this muscle from a frog and seeing how quickly, maybe contraction speed is the only thing that you have, and that ultimately sets the nomenclature moving forward. But at this point, I think that we know a lot more, and because it's a bit of a misnomer, people do take this the wrong way.
Right. So continuing with that, there are better ways of differentiating these muscle fibers right now. And this is something I actually did read about last night. And we're not going to dive too deep into this because you don't need to know about myosin, ATPase, and all these sorts of things. But what they're tending to do now in order to differentiate the different types of muscle fibers is it's a biochemical process. So it's a histochemical staining. They basically take a small piece of the muscle, they stain it, and then they're basically staining for different chemical properties in the muscle fiber, and that allows them to differentiate. And there are different methods. And what I didn't know until last night is there are 3 main methods. We'll really just talk about the one that's used now to differentiate these muscle fibers, and they don't perfectly line up.
Mm-hmm.
So one of the first ones was the ones that identified the type 1, the type 2A, type 2B. It actually identified 7 others. So there was also a 2C, a 1C, I think there was a 2AC, and kind of goes on like that. But that's when they originally said, hey, there's these type 2Bs in humans. The newer method that's now kind of the gold standard is they look at what's called the myosin heavy chain in the muscle, so MHC. And with that, they discovered, hey, we definitely have the type 1. We definitely have the type 2A. We definitely see in animals the type 2B, but we have never seen a 2B in humans.
Mm-hmm.
And so what you see in humans is a 2X.
Yep. And that myosin heavy chain that Trevor is talking about, you can kind of think of it as the structural backbone, the spine, so to say, of each muscle fiber.
Right.
And we don't necessarily need to get into contraction or the structures any deeper than that, but it is a physical structure within the fiber itself.
Yep. But I would say the best way to look at these muscle fibers is how they produce energy. There's other ways to look at them as well. We actually have a big chart here. So different ways they differentiate are size of the motor unit, resistance to fatigue, basically how long it takes them to fatigue, how much force they can produce, their mitochondrial density, capillary density, oxidative capacity. But what I really want to dive into is that how they produce energy. So we've said on the show again and again and again, you are never just producing energy aerobically. You are never just producing energy anaerobically. You're always using a mix of these systems. But when you dive into individual muscle fibers, it gets closer. I'm still not going to say it's black and white, but it gets closer to being black and white. So when you are diving into that type 1 fiber, that slow twitch muscle fiber, it has a whole lot of aerobic machinery.
Mm-hmm.
It has to have some anaerobic machinery because you need the end products of anaerobic glycolysis to power oxidative phosphorylation. But that slow twitch muscle fiber is a huge aerobic animal, doesn't really try to rely too much on anaerobic metabolism. When you get to those 2Bs that humans don't have, my understanding is they have no aerobic machinery. They are purely anaerobic. And then when you're talking about, 2X is the closer to the 2B, so it has a lot of anaerobic machinery, but it still has some mitochondria, it still has some oxidative potential. And then you have those 2As, which my professor described it as the mimicker.
Mm-hmm.
It has both, and it can kind of go back and forth. It can become more anaerobic if you're doing a lot of strength, explosive type work, or it can become more aerobic if you're doing a lot of endurance work.
Yeah, those 2As, I think structurally they tend to resemble more like the 2B, right? In terms of they're a bit larger, in terms of their cross-sectional area, their twitch speed, so on and so forth. But machinery, as we're calling it, in terms of metabolism, they're a bit more similar to the type 1, the slow twitch fibers, which means that they have the ability, especially with training, to do things in an aerobic oxidative manner.
Yep. So we talked about this in a past episode, and this was something I only read a few years ago and found really interesting, is they were looking at what was happening physiologically in the body when somebody tapered for an event, when an endurance athlete tapered for an event.
Mm-hmm.
And one of the biggest changes that they saw was in these 2A fibers. When you tapered, their aerobic potential went way up.
Mm-hmm.
And in this study, at least, they said that's really what you're seeing with this taper, why you suddenly have just this ability to go harder that you didn't have before the taper.
Yeah, it's interesting. Let's do a little bit more comparison here. And when I talk about the metabolic machinery, and let's use the 2A fibers, I think, to help outline the differences in 2B and the type 1 slow twitch. When we talk about things that are going to increase your aerobic ability, right, we're talking mitochondria and then the capillary blood supply. The type 1 and the 2A both have relatively high amounts of mitochondria and the blood supply to feed them, where that 2B, it doesn't have much of that going on at all. When we talk about myoglobin, right, which is the molecule that is essential for moving oxygen, it's like hemoglobin in your blood, but it's the hemoglobin that's in your muscle, so it's called myoglobin. Again, an oxygen-carrying device is a high in the type 1 and high in the 2A, but low in the 2B. So that's where they're very similar in terms of their metabolic machinery.
So I'm going to do a little tangent here just because I think this is really cool. And this is a theory, but I really like this theory of how we got mitochondria. Because in these muscle cells, basically mitochondria, and there's disagreements on what mitochondria look like, but they're generally drawn as these little oval-shaped things. But they're almost kind of a mini cell within the cell. And they have their own membrane, they actually have some of their own DNA. And that is where all of the aerobic energy production occurs. So outside in the cell, that's your anaerobic machinery. And then it's inside the mitochondria that you have the aerobic processes happen. And the theory behind this is you have to look way, way back in the Earth's history. There was life on Earth for a long time before the Earth had an atmosphere. So the original single cells that you had in that primordial goop were entirely anaerobic. They had no aerobic machinery at all. Then the Earth developed an atmosphere, and the theory here is the first organisms to develop aerobic machinery were bacteria. And at some point, that bacteria managed to work its way into these anaerobic cells, and they developed a symbiotic relationship, so they stayed within the cells. And mitochondria are what remain of those bacteria. Mm-hmm. And that's the explanation why mitochondria actually has some of its own DNA.
Yeah, I've heard the same. I have no way of going back in time and proving that. It's an interesting theory, but I don't know what to do with that.
It's kind of a cool theory.
It is kind of a cool
We're not going to do anything with it. It's just a cool theory.
Yeah. So let's get back to these fibers, because I think that functionally the biggest difference that people need to know about is the strength of the fiber, right, yes, Trevor?
That's another big difference.
And really, when we talk about slow twitch fibers, we're talking about fibers that are not very strong. And when we're talking about fast twitch fibers, we tend to talk about fibers that are more strong. Now, of the fast twitch, our 2X are going to be the stronger of the two. But what I found really interesting, and I didn't realize this until I was just doing my research, per size of fiber, all the fibers are the same. Ultimately, what's different is that our fast twitch, our 2A and our 2X fibers are bigger than our slow twitch fibers are.
Cross-sectional area.
And so they're stronger because of it. I always assumed that the fibers were stronger regardless of their size. Like, you know what I mean? And so that was a really interesting finding for me. So I'm glad that I went back and looked at all this.
Yeah, your actin-myosin cross bridges, they're all basically the same. It's just how many of them you have.
Correct. Yep. Nope, definitely.
So another quick tangent here. One of my all-time favorite interviews was Cancellara, and was talking to him about a bunch of things about training. He was a very smart guy, but never studied physiology in his life. So it was great hearing him describe things. And I asked him if he had anything else to say, and he goes, yeah, this thought I've always had that riders like me, and I know my accents are horrible, but go with me. He goes, riders like me, I think we have small muscle. Well, sprinters have real big muscle. And I'm like, are you talking about slow twitch muscle fibers and fast twitch muscle fibers? He goes, yeah, don't know what that is, but small muscle.
Perfect. And he's not wrong necessarily, right?
No, he's not. The other fun thing about hearing him say that is look at a picture of the guy. He did not have small muscles.
No, he was not
a
small.
Beast.
Yeah, I agree.
So, but yeah, I mean, these are the better differentiators between the muscle fibers versus describing them as fast twitch and slow twitch. Even though that's accurate, I would say these are the things to think about when you're trying to differentiate the fibers. How strong are they? How good is their aerobic versus anaerobic machinery? Another place where this is really important, because we've been talking about this a little bit, we've been talking about lactate. And this is another big differentiator. Slow twitch muscle fibers love lactate because lactate is that precursor to the whole oxidative phosphorylation. So they are a consumer of lactate. Your slow twitch muscle fibers, if they see lactate in the blood, they'll suck it up and go, thank you, I need this. Those big more anaerobic fibers, so your 2X, they produce a lot of lactate because there's another debate, but I'm going to say lactate is the primary end product of glycolysis, and they got nothing to do with it. So they pump it out of the cell, and then the slow twitch muscle fibers take it up and say, thank you very much.
Yeah, Trevor, you're talking exactly about lactate shuttle theory that we talked about back in episode 281, if anybody wants to listen to that theory that was developed by George Brooks, and then the work was further continued with Inigo San Milan as well. Yeah, you're entirely right. And it's interesting, I think, for people to see now at the fiber level how that is occurring and how we're able to shuttle out of a predominantly anaerobic-based fiber, a fast twitch fiber, into a slow twitch, an oxidative and aerobic fiber.
And this is really important because if you take a basic physiology class or biology class, they'll always draw on the chalkboard or put up a picture of glycolysis, and they'll show up the end product of glycolysis is lactate or pyruvate. The reason I say the primary is lactate because pyruvate can't cross the mitochondrial membrane, only lactate can. So if it's going to go into aerobic metabolism, it has to at some point be converted into lactate. And then once it's in the mitochondria, it gets converted back to pyruvate. But the important thing here is they'll always show you a picture of glycolysis and then an arrow pointing down to the Krebs cycle and then oxidative phosphorylation. And the implication is this is all happening in the same cell. But it's really important to understand that there's a little bit happening in the same cell, but really you need this lactate shuttle because you have some muscle cells that are producing a whole lot of lactate and they can't use it. And you have other muscle cells that don't produce a lot of lactate, but they can use a lot of lactate. Before we move on, I think there's a couple last characteristics to point out. One is fatigability. Slow twitch muscle fibers, and this is a simplification, technically don't fatigue. They can keep going. And there are some slow twitch muscle fibers where that is true. Think about your heart. Your heart is basically all slow twitch muscle fibers. And if they ever fatigued, you are in big trouble because then your heart stops. So those muscle fibers are contracting your entire life. Slow twitch muscle fibers in your muscle, technically, yes, they don't fatigue, but realistically, they'll start over time experiencing muscle damage. They'll start having fuel issues, so they can fatigue, but they can go a very long time. When you're talking about the 2X, they are very powerful, but they fatigue really fast. 2A, kind of in between. They can certainly last more than the few seconds or a minute, but they can't go the hours and hours and hours that a slow twitch muscle fiber can go. Anything to add to that, Rob?
No, I don't think I have anything to add to that, but I do want to address a question that I think a lot of people are probably thinking and asking themselves right now, and that is, well, gosh, all of these different muscle fibers have all of these different traits and characteristics. What's going on inside of me, right? Do I have different muscle fibers than you do? And what I'll say is that most people, if you take just a cohort of individuals, hundreds and thousands of people, and you look at their fast and their slow twitch muscle fiber distribution, these are just normal people. They're not world champion sprinters. They're not world champion marathoners. most people, I think, tend to have a relatively 50-50 distribution of these fibers throughout their body. But as we're going to talk about in the future, training can certainly influence that, at least the expression of that. What I was trying to do in the background real quick was look, I have a 23andMe account, and I believe in there somewhere is, a guess as to whether or not I'm likely to have more fast twitch fibers than slow twitch fibers. Genetically, I think that we can certainly tease out some differences between people. But what I'll always say with genetics is it is very, very complicated. And we can't necessarily just look at one part of your DNA and know if you're going to be a world-class sprinter or not. And so I would caution people away from doing things like.
Yeah. And it also gets complex as you pointed out, different muscles are going to have different compositions in everybody. You talked about the soleus and the gastroc. In everybody, whether you're a sprinter or a marathon runner, that's still going to hold true that the one has more slow twitch than the other. I'm actually looking at a really interesting chart from one of my old textbooks here that talks about the distribution you're going to see in different athletes. So athletes who tend to be higher ratio of slow twitch muscle fibers tend to gravitate towards endurance sports. Athletes that have a higher ratio of the 2X, 2A tend to gravitate towards the sprint sports. But even saying that, they have this graph here, and what's really interesting is they don't say which particular muscle they're talking about in this graph. Mm-hmm. So I don't know what muscle they're talking about, but they're showing the percentage of slow twitch muscle fibers in some muscle, I'm assuming somewhere in the legs. And you look at long distance runners, they tend to be in the range of 50 to 80% slow twitch muscle fibers. But let's go all the way down to the bottom and look at sprint runners, like 100-meter sprint runners. They tend to be 35% to 65%.
Yeah.
So less, but it's not like you're saying the long distance runner is 100% slow twitch and the sprinter is like 5% slow twitch.
Correct. Yep.
There's a lot of overlap there. For both beginners and veterans, polarized training is the best way to get and stay fast year after year. And this is the perfect time of year to be thinking about how polarized training can help you. In our new guide featuring Dr. Steven Seiler, explore fascinating and helpful topics like how polarized training is different from sweet spot, how to bust out of performance plateaus, how to polarize all season, how to build durability, and how to time your high-intensity work. With the complete guide from Fast Talk Labs, you'll have everything you need to polarize your training like a pro and unlock your elite. Learn more at fasttalklabs.com.
Well, Trevor, let's get to some more fun stuff.
Recruitment?
Yeah, let's recruit people to the muscle fiber army.
Absolutely. So I love learning about the recruitment of muscle fibers. This is kind of cool to me. So a really important thing to understand about all these muscle fibers is a muscle fiber is an all or nothing thing. A single muscle fiber can either contract maximally or not contract at all. It can't go, I'm going to do a 50% contraction here. And to take that a step further, you're talking about the whole motor unit. So if the motor unit innervates 6 muscle fibers and that motor unit activates, all 6 of those muscle fibers are going to contract. And they are going to contract maximally. The best way I had it described to me, which I always love to use, but this was a professor teaching this in a class. He picked up a pencil and then lifted it and said, so if muscle fibers contract maximally, why didn't I just punch myself in the head? How can I control the effort that I put in? And that is the whole theory of recruitment. You control the strength of the contraction of the overall muscle by how many of these motor units contract. So if you're just picking up that pencil, maybe 1 or 2 motor units are contracting. So it's just a few fibers that are going to contract, and it's going to be a slower, easier effort.
Yeah, I've always explained this by using an example of a car on a hill. And let's say that car broke down, and you have to push it to the top of the hill to get repaired. Well, if it's just you and you're behind that car, you are not strong enough, right? As soon as you take the brakes off that car, it's going to roll backward over you, no matter how hard you're pushing, because you're pushing 100% with all of your strength.
Yep.
That's how we lower a weight down. We don't recruit enough muscle fibers, and the weight is just stronger than the muscle is, and so gravity pulls it down. So now you get a friend, and the two of you are behind the car, and you have just enough strength when you're both pushing as hard as you possibly can that you just hold the car in place on the hill. You want to push that car up the hill, you get a third friend. Now the three of you are slowly pushing the car up the hill. You want to run that car up the hill, then you get 100 friends. And all 100 of you pushing move that car so fast, it's like it's not even there. By changing the amount of fibers or motor units that are being asked to help out, that's how we're able to grade our strength.
You know what the biggest issue with that car was?
What?
Used vegetable oil. Call back to our fringe episode 2 weeks ago. Sorry, I had to do it. It's early in the morning.
Next.
Yeah, so that's exactly the way it works. And now here is what is important. And to me, this is one of the biggest, most important thing to know about the different types of muscle fibers is there is a recruitment order. So if you're only picking up that pencil and recruiting 1 or 2 units, you're not recruiting those 2x units. You are going to start with the type 1 fibers, with those slow twitch muscle fibers. And basically, as you're increasing the effort, you're going to recruit more and more and more slow twitch muscle fibers until they are all recruited. Then you're going to start recruiting the 2As. Then you're going to start recruiting the 2X. And there's a reason for this. Again, remember the type 1s don't fatigue. So there's no cost of using those. You want to save your 2X for when you have to do that big effort. So your body's being smart and saying, okay, I don't have a big effort here. Let's use the type 1s because then I'm still going to be fresh as a daisy if I have to do something else. And it's only going to bring in those stronger, more anaerobic, more fatigable muscle fibers when it has to.
Yeah, and that it makes a lot of sense when we do think about this from the strength and the fatigability side of things, that we're using the less strong fibers initially. No reason to go straight to the super strong ones. And then at the end, when you're working as hard as you can, bring in the weak ones. That doesn't make any sense there. But what's interesting to me, Trevor, is, and I didn't know this stat either, at any one time, right, we would assume, based on what we just said, that when you are pushing as hard as you possibly can, then you're recruiting 100% of your muscle fibers. Not the case. At any one time, we can maximally recruit only about 1/3 of our muscle fibers. But that makes sense because if we were able to recruit absolutely everything at once, then we would get one super strong impulse. We would never be able to sustain that force, or our movements would be really herky-jerky. And so by recruiting some fibers here, switching off to other fibers, replacing them as we start getting a little bit tired because we're trying to hold up the bed so that my son can get his toys out from underneath it. That's neither here nor there. I don't know why I had that example. But this is also explains why at times and in certain circumstances, people can have superhuman strength, right? Baby stuck under a car, you can lift that car off the baby, because when adrenaline is flowing and you have all of these other neural things happening in your body, you're able to recruit more fibers than you typically could for a one-off feat of strength. But that's going to open you up to things like injury, because now you're putting so much force through your ligaments and tendons, so on and so forth.
You are going to be doing some tearing. It's going to be bad.
But you're going to lift up that heavy thing because you have to.
So the one image I can't get out of my head when we talked about this recruitment and using the type 1s first to save the big strong fibers. Mm-hmm. I was going back to your analogy of pushing the car up the hill, and I was just picturing this 100-pound nerd pushing the car with Dwayne Johnson on the side of the road going, come on, just push. I don't want to fatigue.
Yeah, I guess that's true, right? And that is probably a more accurate way to describe this. I'm glad that you added that in, because I'll add that into my explanation that the weightlifters and the football players, they're just sitting on the sidelines waiting to be called on, just laughing, watching the weak fibers trying
to run over by a car.
but that skinny person, I'm not going to call him a nerd, that skinny, less strong person can push for a really long time without getting tired, Trevor. Just saying.
I don't mind calling him a nerd, because let's face it, Rob, we're nerds.
I'm not a nerd.
Okay, you can deny it. I have accepted my nerdness a long time ago.
Well, you are like 100 pounds compared to me, so.
Yeah, there you go. Remember, I used to be a football player. I was a football lineman in high school. Nobody believes me on this.
Trevor, before we move on, I want to touch back on a statement that you had made earlier, an example of the conversation. At what cadence do we switch over from our slow twitch to our fast twitch fibers? And that is important because Well, as we mentioned before, is just not the case, right? In all honesty, let's be honest. When we're talking about 60, 70, 80, 90 RPM, we're really not talking about a very big change in speed. And so there could be some movements that are so fast that they have to be fast twitch fibers. But running cadence, cycling cadence, that's not it. Ultimately, what we're doing is this. At low workloads, we do not have to put a lot of force into the pedals to push on that pedal. When we're walking, we don't have to be putting a lot of force into the ground to go walking speed. And so based on what we just discussed, the initial fibers at low forces that we're going to recruit are those aerobic type 1 oxidative fibers. As we pedal harder to bring our watts from 100 to 150 to 200, whatever it is for you. As we move into a more fast running speed, we have to be pushing harder. And eventually we get to a point where those type 1 fibers, we're asking all they can give and they just have nothing else to give.
Right.
So if we need to push a little bit harder, we need to begin recruiting those stronger muscle fibers into our 2A fibers, right? Those are the ones that are metabolically like the slow twitch, but structurally like the 2X fast twitch fibers. This continues on until we are recruiting the biggest, baddest fibers that we have, because now we're trying to push 600 watts up a hill because it's so steep, because we're trying to sprint a 100-meter dash as fast as we can. We need all the fibers to do that.
Yep. And I think that segues to a theory here. And Rob mentioned he looked for any research on this last night and he couldn't find it. I do remember reading about this years ago, so my memory might be faulty, but this at least has some intuitive sense. So we've talked a lot about the fact that there's two kind of breakpoints as your wattage increases, or if you're out running, as your speed increases. So there's that VT1, or your aerobic threshold, and there's that VT2 and your anaerobic threshold. And if you look at a lactate curve, your lactates are very, very low. And then when you hit that VT1, that's where you start to see the lactate curve kick up. And VT2, or anaerobic threshold, is where the curve really kicks up and you really start producing a lot of lactate. And one of the theories behind this is those are the breakpoints of when you start recruiting the different fibers. It's not perfect. It's not like you're only just recruiting slow twitch muscle fibers and then all of a sudden you're recruiting 2As. But as you remember, we just talked about the fact that your slow twitch muscle fibers produce very little lactate. So they're not pumping any lactate out into the blood. 2As will produce lactate and they will pump some out into the blood. So it makes sense that as long as you're mostly just using slow twitch muscle fibers, you're going to see no increase in your blood lactate. Once you start recruiting those 2As, blood lactates are going to start going up a bit because they're pumping it out. When you hit those 2X, they are giant lactate producers and they can't use it, so they're pumping a ton into the blood. So that's when you're really going to see those lactate levels go up.
Yeah, I think it's important, Trevor, to say that it's not a perfect line, but it does kind of intuitively make sense. We know that there's some other things going on there too, right? Because the liver and the kidneys, they're able to take up some lactate as well. And at higher intensities, blood flow there slows down. And that also is part of the reason why the graph gets so steep at the end. But it does kind of make intuitive sense. And I've always worked off of that theory, but I've never looked until last night for the research to back it up. And I personally couldn't find any. So I'm going to do a little bit more digging. Hopefully I can find something. And if I do, we'll make sure that that stuff gets into the show notes.
Yep. You know, another thing that I think is really important here that you can understand in the context of muscle fibers is we've talked a lot in the show about the importance as endurance athletes of developing fatigue resistance. Mm-hmm. So remember, slow twitch muscle fibers are essentially infatigable, but they can get damaged. They can start having fuel issues. So if you are not a well-trained athlete and you're going out and doing a long bike ride or a long run, there is a point where, let's say you're just going at a steady pace or a steady wattage. There is a point where those slow twitch muscle fibers aren't going to be able to produce all the power for you anymore. And you're going to have to start recruiting those 2As. And if you're really out of shape, those 2As are going to start fatiguing and you're going to start having to recruit those 2X. So even though if you're on a bike and the power was steady the whole way, At the start of that ride, you're just using slow twitch muscle fibers. You're down in that zone 1, zone 2. By the end of that ride, you're recruiting a whole bunch of type 2A and 2X fibers, and you're hitting a whole different system.
Mm-hmm.
You're not training the same thing at the end of the ride that you were at the beginning of the ride. And we talked about this before, that's actually one of the benefits of a long ride, is forcing those 2As to work aerobically and training their ability to not fatigue.
Yeah, Trevor, another interesting thing that ties recruitment and training together is if you think back to our episode 251, which is the time at VO2 max episode that we did based on Dr. Bent Ronstadt's research. A big part of the reason he's a proponent for time at VO2 max is that, and this is where the recruitment is tied together, at VO2 max is an intensity at which we are maximally calling on muscle fibers. Maybe not maximally, I shouldn't say maximally, but we're calling on significantly more muscle fibers, which is bringing more fibers to be trained into the equation. If we're only ever spending time at low intensities, short of going for a very long duration like you're talking about, then we're kind of training the same fibers over and over again in a very moderate sort of manner. And we have to be at these VO2 max level intensities so that we're recruiting all of our aerobic fibers together to accomplish that work and giving them all a training stimulus.
Right. And, one of the biggest tricks, I think, in really producing training gains, going back to that whole study about tapering, showing the biggest thing you see in taper is getting those 2As to work aerobically. I think this is something you generally want to do in your training. Mm-hmm. As we said, those 2As are mimickers. They can be more anaerobic or they can be more aerobic, and you want to get them to be more aerobic.
November. The air is crisp, the leaves are falling, and I get to take a break from riding my bike. Now is a great time of year to rest and reflect on the past season. Visit Fast Talk Labs and take a look at our pathways on recovery and data analysis. These 2 in-depth guides can help you get the most from your off-season. See more at fasttalklabs.com/pathways.
So going back to, I was a football player in high school and then became an endurance athlete. I noticed that issue in fatigability. I was actually explosive as a football player, but when our coach made us go out and do a 2-mile run, it killed me.
Looking at you today, Trevor, there's no way you were a football player. I literally don't believe that that is part of your history. And the only thing that can explain this to me is answering this question. Can muscle fibers convert? Are you no longer the same person that you were when you were a football player?
And here is the key question that there is probably some debate over. When I first started studying physiology many, many years ago, I was taught they really can't convert. But that was a while ago. What I have personally been seeing, and Rob, let's address this. I know you were looking into this last night, is yes, they can convert. So no, you can't be a football player, go and spend a week going for long bike rides, and all of a sudden you're all slow twitch muscle fiber. That's not going to happen. Nor can you be that skinny little endurance athlete going to the weight room for a week, and all of a sudden now you're buff and you got a whole bunch of those 2Xs. It's not quick, it's not simple, but they can convert.
Yeah, I think that that's the same sentiment that I have based on my research. And this is an area where I think that I'm kind of a living example of the ability to convert, right? If you really were a big, bulky football player, I'm still waiting for pictures. I'm still waiting for some character witnesses. At least today, you are no longer a big, bulky athlete, and you're a pretty solid aerobic functioning individual, right? You've reached relatively high level in cycling. My background to you is somewhat similar. I was a hurdler and jumper, high school and college, very sprint focused. And I have been able to improve my ability aerobically. I really enjoy doing long multi-day mountain bike races, so on and so forth. But I still retain a lot of my sprint capability, right? You know, I cannot train to sprint at all and still hit easily over 1,400 watts, right? I know that that's not a lot in the whole scheme of things, but it's a lot more than most people, and certainly more than most people that train for that. But I have not been able to shift myself quite as far as you have, but I've definitely been able to shift myself quite a bit. And so there is certainly a range, I think, in what is achievable through training in terms of a fiber type conversion, or at least characteristic conversion.
Yep. So I've seen this in textbooks, and this might be outdated, but it's something I've always said to people, which is the expression goes, all training causes a conversion from fast twitch to slow twitch. So training causes conversion from 2X to 2B to type 1, which is why you probably can put out your best sprint power coming off of the couch. Mm-hmm. I've always seen this. When I take my off season and I don't get on the bike, my ability to time trial, my endurance are all tanked, but I can always put out my best sprint power. So it's really, you want to get those 2X, it requires a lot of rest. And the example I always point to is look at the best sprint animal in the world, the cheetah. Mm-hmm. Spends a lot of time sitting around.
Yeah, I think it's interesting. I looked through, almost a dozen studies last night on this particular topic, and they, in my mind, confirmed that conversion is possible, but what that conversion is looks very different based on the situation. One of the early studies looked at riders doing on a cycloergometer, I believe 5-minute efforts at 95% of their VO2 max power or whatever, pretty standard VO2 max level workout. And they saw conversion of muscle fiber from 2X to 2A, but also from type 1 to 2A, right? So we're kind of all roads are leading to that 2A situation. I looked at another study that looked at beginning individuals who were not necessarily athletes. They had kind of a 50-50 fiber type distribution. And they, I think if I remember correctly, maintained their 2As, really reduced their 2Xs and increased their type 1s, right? So 2As stayed kind of the same based on that training. Their really strong fast twitch fibers came down, and then their slow twitch came up. So it really depends, like you were saying before, Trevor, the types of training that people are doing and the duration that they're doing that training for, right? And that's where I think maybe some of these studies were a bit confusing, because if the study isn't set up correctly, it's very easy to say, oh, there was no change, there was no difference, right? And so if you do it with the appropriate subjects who are in appropriate types of workouts for an appropriate duration, then I do believe we get a lot of good science that says, hey, yeah, we are definitely seeing some structural changes and the muscle fiber characteristics changing along with that.
Yep. So I think another thing that people get confused, we're talking about this fiber conversion. As I said, it takes a long time. We're measuring this in years. I think when you see that shorter term transition, some of these things that we were just talking about, I haven't seen a study to say this absolutely, but this is just intuitive, that more of what you are seeing is those 2As with their capability to mimic. So if you're seeing, hey, this person's really moved from a much more explosive anaerobic type phenotype to that more endurance type phenotype, I think probably what you're seeing is a lot of those 2As moving from being heavily anaerobic to being much more aerobic in their capabilities.
Well, and I think that this backs up something that we talk about a lot here, and that is if we look at research on high-intensity interval training, we can see relatively large changes in a relatively short amount of time, especially because that research is being done on maybe an active but otherwise sedentary population, not a highly trained population anyway. And so we're able to see that relatively fast conversion of the 2X to the 2A because the equipment is all, for the most part, there already. But the longer term stuff that we're talking about, right? We talk, it takes years and years and years of steady base, steady zone 2 training to really reach your potential in terms of an aerobic individual. And that is probably, again, related not just to the training of those muscle fibers. That in itself might be able to happen quickly in terms of mitochondrial biogenesis within a type 1 fiber. But over years and years, we're getting conversion of that fast twitch fiber to slow twitch. And that's the continued improvement that we see that really makes somebody, an appropriate endurance athlete.
Yep. Now, the last thing I'm going to throw into this, even though Rob and I have been sitting here saying, yeah, they can convert. I read actually a very recent study a couple nights ago So they took endurance athletes and they took strength athletes and we're looking at the differences in their fiber type. But what they dived into is differences in genetics, differences in the DNA, and differences in microRNA. And they did show, there are differences. It is somewhat hard-coded in your genes. So I think the answer here is, can conversion happen? Yes. But we are all born kind of more one way or more the other. And if you are born with the genetics to be that big, explosive, anaerobic animal, you're probably never going to win the Tour de France.
I would probably agree with that.
And vice versa.
Yeah. Something else I think that's interesting to point out is that, as we mentioned before, at this point in history, we tend to be calling muscle fibers based on that myosin heavy chain nomenclature, right? The structural. But it is possible that we're seeing fibers have metabolic changes without the structural change. And so we might say have performance improvement or performance changes, but our fiber typing doesn't necessarily change because the structure of the fiber is the same, even though its metabolic activity is a little bit different. So perhaps depending on the type of staining or the method that's being used to classify, we may or may not see some changes, and that ultimately accounts for different research results.
Now, I think there is one last thing to cover here, and this is an effect that you see with aging. This effect is called motor unit remodeling. So as we were talking about early on, you have this motor unit, which is a nerve that then branches out and it connects to multiple fibers. And as we said, when you recruit a motor unit, you recruit the whole thing. So that nerve fires and all those fibers will contract. What you see over time is that you see basically orphan fibers. They disconnect from their motor unit for a variety of reasons, and then you have a fiber that cannot contract. But it will eventually reinnervate. So this is the remodeling. It will connect to another motor unit. And for whatever reason, and I haven't dived deep enough into this research to understand why, almost invariably, you see it connect to a slow twitch motor unit, not a fast twitch. And so something you do see in aging, particularly, you see this in endurance athletes all the time. The first thing you lose is your explosive sprint power.
Yep.
But older endurance athletes are just animal. I mean, this is why people who do those ultra endurance events like Race Across America, you're considered in your prime in your mid-40s because you just become these aerobic monsters. And this is part of the explanation behind that is what you're seeing is this deinnervation and some fast twitch muscle fibers are connecting to a slow twitch unit, and then they do convert to a slow twitch muscle fiber.
And it's funny because, Trevor, I had no background knowledge of this concept at all because, frankly, I'll never age, and so it doesn't matter to me that this happens. I kid. I'm getting old real fast. But I did know that, and I don't even know how I knew this, that if you connected a fast twitch fiber to a slow twitch motor unit, that fast twitch fiber would then convert into a slow twitch fiber, which is just like baffling and mind-blowing. But I think ultimately it makes sense based on the previous conversation we've had.
So here is where exercise is so important for health. Because what they have shown is that when you are training and training regularly, you see a lot fewer orphan muscle fibers. So you can't stop it, but you can slow down this effect. The other important thing to remember here is what happens when you have a lot of this remodeling is you start losing motor units. What will happen is it will connect to an existing motor unit, and that motor unit will start increasing the number of fibers connected to it. And what you will have in any given muscle is fewer motor units that are innervating a lot more fibers, which means you lose fine control. So then when you go and try to pick that pencil up and pick it up slowly, you might not be able to quite pick it up at the pace you want.
Yeah, or just all of your movements are going to be less smooth, right? Because you're not able to be grading that force. Maybe there's going to be a little bit more of a shudder in somebody's movements. Interesting.
And so this is something you see in aging with people who aren't physically active, is you see that reduction in the number of motor units. And so this is why you see them, elderly people who unfortunately haven't been too healthy, they tend to shuffle. They tend to have those problems with the fine movement. This is one of the reasons behind that, at least from what I have read. And so this is what makes exercise really important. And if you want to avoid becoming that pure slow twitch, that's all your nervation type person, this is why getting in the weight room, particularly as you get older, is so important because you need to protect those fast twitch motor units.
Interesting. Yep. Wow. Heck of an episode.
That was fun. Did we leave anything out?
Well, I mean, I think that we explained about 1% of it. So yeah, we left 99% out.
Good point.
Let's be honest there. But no, I think that we covered that 1% pretty well. And I learned something. It took until the very end of the episode for me to learn it, Trevor, but I learned something today.
I hope everybody got something out of this. I hope we didn't get too deep in the weeds, as you said. You know, we were trying to give the basics here. We probably at the end got into a little heavier on the science. But you're right. You know, when you start diving into this, it gets complicated. You know, realistically, we keep talking about type 1, 2A, 2X, but there's all sorts of variations within there. You can get real complicated with this.
All right. Well, maybe we should do this again.
I think so. So give us your feedback. If you like this, let us know, and let us know other basic topics in the physiology you'd like us to cover, and we can do more of this.
Yeah, let's talk about excitation, contraction, and decoupling. That sounds great. Let's do that next. No, not basic?
I had to think for a minute about that. We should probably do it because I need to refamiliarize myself.
It's all good.
That was another episode of Fast Talk. Subscribe to Fast Talk wherever you prefer to find your favorite podcast. Be sure to leave us a rating and a review. The thoughts and opinions expressed in Fast Talk are those of the individual. As always, we love your feedback. Tweet us at Fast Talk Labs or join the conversation at forums.fasttalklabs.com. And of course, you can learn from our experts at fasttalklabs.com as well. For Rob Pickels, I'm Trevor Connor. Thanks for listening.